analysis, where I discussed how you can reduce various variables in dimensionless parameter, and then ultimately you will see that out of various variables you can reduce any particular equation in 2 or 3 dimensionless number. So to conduct dimensional analysis today today I'll be talking about some Buckingham pi theorem. First let's talk about Buckingham pi theorem method. So I'll talk about some fundamentals regarding this Buckingham pi theorem. So to conduct this dimensional analysis on a given problem, the first step is to identify the variables that affects the system. So first you identify variables, right? I'll tell you with the help of some examples also. So these must be determined by the judgment of an investigator or exercised in the length of such knowledge of mechanism that is available or during the experiments. So for example, consider again the heat transfer from the walls of a pipe to the fluid flow in the turbulent flow condition through inside the pipe wall. So we know that the heat transfer process is affected by various variables, right? So if I am talking about the heat transfer process, that is a function of various variables like pipe diameter, already in the previous lecture, fluid velocity, fluid viscosity, density of fluid, heat capacity, and thermal conductivity, and then there comes a heat transfer coefficient as well. That is another important parameter. So these equation describing the heat transfer process, that can be written as that is a function of, let's say, heat transfer diameter of pipe. Here I'll use a notation in capital D, and then I'll use here also in the capital D U, viscosity, density, Cp and K, that will be equals to 0. So these are the different techniques. There are different techniques of conducting the dimensional analysis, right? So the method that we are going to study here in this lecture is Buckingham pi theorem, and that is based on the fact that the functional relationship between and relation required to describe a system that can be equivalently written in terms of n minus m dimensionless variable, n minus m dimensionless group. So let's say you have n variables and m number of primary dimensions. So let's say I am assuming n is your number of variables, m is your, let's say, m is your primary dimensions, right? M is your primary dimensions. So basically what you can say here is that you can that system can be equivalently written in the terms of n minus n dimensionless group. So from here you can write n minus m dimensionless group you can form. How you can form n minus n dimensionless group, I'll tell you. Just try to understand with the help of some example. So let's say if you have n equals to 7 here and m equals to 3, right? So how many dimensionless group that you can make here is n minus m, that is equals to sorry, let's say m is 4. So 7 minus 4, that is equals to 3. So we can write a relationship for heat transfer as a function of 3 dimensionless group, that is pi 1, pi 2 and pi 3, and we can directly write f dash of pi 1, pi 2 and pi 3, that will be equals to 0. And how we can write these things, I'll let you know here. So let's try to understand another example of right. So what I have told you, you can make 3 dimensionless number here, and when we talk about the heat transfer coefficient, we can write Nusselt number, that is equals to hd by k, that is your one dimensionless number. Then we can also define Prandtl number, that is equals to mu cp by k, and then another dimensionless number that you can define as rho u d by mu, that is Reynolds number, right? So all these numbers are called as the dimensionless number, and in order to understand the heat transfer coefficient, you have reduced 7 variables in only 3 dimensionless variable, and we have obtained these things using the Buckingham pi theorem, right? So this is the overview how Buckingham pi theorem works. Now I'll be explaining you with the help of another example where I'll calculate how you can actually derive this kind of equation. So let's talk about another example of the pressure drop in a pipe, right? Delta P. So we are going to solve this particular problem. So pressure drop in a circular pipe basically depends on following variables like your fluid velocity density rho, fluid viscosity mu, diameter of the pipe d, fluid velocity u, and then pipe length. So let's say if a circular pipe is there, right, all these variables you will see. So if I am assuming this is the length of the circular pipe, and if fluid is flowing with the velocity u, okay, and if the diameter of the circular pipe is d, and I want to find out what is the pressure drop, right? So using the Buckingham pi theorem, we will obtain how many dimensionless group that can govern this particular system. Okay, so let's try to understand that thing. So first I'll identify all the variables. So first we'll identify all variables. So the pressure drop depends upon, let's say, delta P, rho, u, mu, d, and L. So here you can see that total number of variable that I have defined is n, that is equals to 6, right? Now second step is to write the dimensions of each variable, right? So you need to write each variable. So let's try to make a table. Let's say this one is your variable, and then there is a dimension. So the variable will be your pressure drop, density, viscosity, diameter, velocity, and the length. So the unit dimension of pressure drop you can write is m, L minus 1, T minus 2. Density unit is m, L minus 3. Viscosity is m, L minus 1, T minus 1. Diameter will be length only. Velocity is L, T minus 1. And the L is your length of the pipe, that is L. So if you see here, how many number of primary dimensions are there? So step 3 is determine number of primary dimension. So the primary dimension here we have observed is mass, that is m. Then there is length, and then there is time. There is no temperature involved, so we'll escape that also, right? If temperature will be there, then there will be 4 primary dimension, but here you can see there is no temperature involved in this. That's why we should not write the temperature now. So the number of primary dimension we have denoted it is as a small m. So this is m equals to 3 and n equals to 6 we have already get. Now fourth step here that we have to do is to calculate the number of pi groups. Number of pi group means number of dimensionless group. So Buckingham pi theorem states that number of pi group that is equals to n minus m, and here you can say that number of pi group will be 6 minus 3, that is equals to 3. So we will obtain 3 dimensionless group here, right? Now choose repeating variable then. So fifth step is choose repeating variable. So the good choice, so repeating variable that will come from the fundamentals only, right? Fundamental dimensions. So the good choice will be your rho, v and d. So that includes m, l and t, time, right? So now we are going to form first pi theorem. So step 6 will be first pi terms. So we will be having your pi 1, pi 2 and pi 3 here, right? So we are going to find out the first pi term. So start with the pressure drop. So let's say your pressure drop, so pi 1 will be equals to what? Delta P into since we have defined rho, v and d, so we will write rho to the power a, v will be here velocity, I'll write here u to the power b and d to the power c. Is that clear? So we know the pressure unit delta P is your m, L minus 1, T minus 2. Density is your m, L minus 3. Velocity is your L T minus 1 and diameter is L. Is that? Now I'll be substituting this into equation. Once we substitute, we will be getting pi 1 that is equals to m L minus 1 T minus 2, that is pressure, then ml minus 3 whole to the power a, then lt minus 1 whole to the power b, then l to the power c, right? So you can also say pi 1 that will be equals to m to the power 1 plus a, l to the power minus 1 minus 3a plus b, and t to the power minus 2 minus b, right? So now we have to make the power in the left hand side and right hand, because this is a physical quantity and already I have told you it should be equal. So from here you will get 1 plus a will be 0, so a will be equals to minus 1, minus 2 minus b will be 0, so b will be equals to minus 2, and minus 1 minus 3a, it should be I have made one mistake over here. So for L it should be minus 2 minus 3a plus b plus c, right? So I can say here minus 2 minus 3a plus b plus c will be equals to 0. So from here I can calculate c equals to 2 plus 3a minus b minus c. So that is 2 minus 3 plus 4. C will not be there. So that will be equals to your 3. Oh, sorry for that. It should be 1 minus 1 minus 1 minus 3a and then plus b plus c. Minus 1 minus 3a, yeah. So I'm really sorry for that. So it will be minus 1 minus 3a plus b plus c will be 0. So c will be equals to 1 plus 3a plus b, that is equals to 1 minus 3 plus 2. I don't know why I'm writing wrong. Minus b. So that will be plus 2, that will be equals to 0. So from here you have got a will be equals to minus 1, b will be minus 2, c will be equals to 0. Right? So now I can write the value of pi 1, that is equals to delta p into a. We know the value of a, right? Rho to the power a. So rho to the power minus 1 and u to the power b. So u to the power minus 2 and d to the power c. So d to the power 0. So the value of pi 1 that we have got, that is delta p divided by rho u square. So this is one dimensionless number that we have obtained using the Buckingham pi theorem, right? Now let's move towards the next thing, that is finding the second pi term. So that is second pi term, that is your pi 2. So how will we find this thing? So again in pi 2 we will write, that is your viscosity into, let's say, rho to the power a into u to the power b into d to the power c. So if you will again calculate all of these things, you will be getting that pi 2, that will be equals to mu divided by rho u d, and that is called as the Reynolds number. So you got the pi 2 as your Reynolds number, that is another dimensionless number. And then we are going to find out the third pi term here. That is your pi 3. So in pi 3 we can write, that is length into rho to the power a, u to the power b, and obviously d to the power c. And once we do the calculation, you will be getting pi 3. The way you have to, I have done the calculation in pi 1 exactly in the same way you have to do calculation in all of these pi 2 and pi 3. You will be getting L by D. So in the final result now, you can see here that we got pi 1, pi 2 and pi 3, that will be 0. That is the equation. So now I'll substitute the value, that is function, that is delta p divided by rho u square, mu divided by rho u d, or L by D, that will be equals to 0, right? So directly we can say that delta p divided by rho u square, that will be a function of rho u d divided by mu, and then there will be L by D, right? So the interpretation that you can see here is the pressure drop that depends upon the Reynolds number in a circular pipe. This pressure drop depends upon the Reynolds number and the geometric ratio. So you had lots of parameters, 7 parameters or 6 parameters were there, and now you reduce the parameter only in 2 dimensionless group, that is the Reynolds number and the dimensional geometric ratio, right? So this is how we have to perform the Buckingham pi theorem to reduce the dimensions for a particular parameter in the system. I hope everything is clear to all of you, and I would like to end the lecture here only. And those who have not subscribed my channel, please do like and subscribe the channel, and don't forget to click on the bell icon, so that if I am putting any new video, that you'll get some notification. Okay. And the most important thing for this particular lecture that I wanted to share with you is that I have designed this course to understand the basic of all concept in this particular stoichiometric and chemical engineering process calculation subject. Because let's say you forgot, let's say if you are in bachelor's second year or first year, and during the course, during the semester you will be having 5 or 6 courses in a semester. So sometimes you don't focus on this particular subject, and this subject is very fundamental. So repeatedly you will be using the concept of this subject in your mass transfer, heat transfer, fluid mechanics, process process dynamics and control, chemical reaction engineering. So I thought to design this course so that if you miss that subject in your college also, so if you go through this video, you will understand each and every fundamental thing of this particular course, so that your subject will be very strong. And when you are writing your semester exam, or you are writing GATE, you are writing BARC, and you are writing any another competitive examination in chemical engineering like HPCLO and GC, this course is really going to help you a lot. And just go through the video, you will feel the benefit of going through this particular course, right? Thank you all.